start. So today we are going to start our PowerPoint presentation on different kinds of logic gates. So here is the content of logic gates, different kinds of logic gates, and conclusion and reference. So now in introduction in logic gates is a building block of a diagram, digital electronic circuit that takes two or more inputs and gives one output for Boolean and etc. Uses of logic gates, basically logic gates include such as multiplexers, arithmetic logic units, microprocessors, and discrete electronic systems. So there are three kinds of basic logic gates. One is OR gate, AND gate, and NOT gate. And then NAND gate is an electronic circuit which is used in Boolean algebra for multiplication. If the two input of A and B both are 1, then the output is high, and otherwise the output is 0. Similarly, here is a truth table of two input AND gate. One is 0 0 0, 0 1 0, 1 0 0, and 1 1 1. Similarly, the three input AND gate is 0 0 0, then the output is 0, and so on. And the IC used in diagram which is 7408, and the OR gate is an electronic circuit which is used in Boolean algebra for logical summation. If two input is A and B which is 0, then the output is 0 which is 0, otherwise the output is 1. And here is the truth table for three input OR gate which is 0 0 0 0, 0 0 1 1, and so on. And here is the diagram of two input OR gate which is 0 0 0, 0 1 1, 1 0 1, 1 1 1. And the IC which is used in OR gate is IC 7433.
In OR gate, if one of the input value is 0, then the output is 1. If the input is 1, the output is 0. The NOT gate is sometimes referred as the inverse because it inverts the output value, because it inverts the input value. The truth table A complement 0 0 1 1 0. The IC diagram of NOT gate. Universal gate is a gate that used to implement any types of implement any Boolean algebra function without needing any other types of gate. That consists one type of gates, then function one type of gates like AND gate, OR gate, NOT gate, XOR. The two universal gates are NAND gate and NOT gate. Why they call universal gates? Any Boolean function can implement using only NAND gate or NOT gate. The simplified circuit is seems to only need one type of gate an entire system. NAND gate and NAND gate consists NAND plus NOT. The output of NAND gate are high if any of the input is 0. These are two input diagram of NAND gate. A dot B complement 0 1 1 0 1 1 0 1 1 1 0. NOT gate consists NOT gate consists OR plus NOT gate. The output of NOT gate are low if any of the input is 1. There is a truth table of NOT gate 0 0 1 0 1 1 1 0 1 1 1 1. NAND gate, 3 input NAND gates, IC diagram, NOT gate, 3 input
exclusive gates. Exclusive gate typically refers to exclusive OR and exclusive NOR gate, which have distinct behavior compared to other logic gates. The two main types of exclusive gates are XOR gate and XNOR gate. XOR gate is a digital logic gate that gives the output 1 if any of the input is 1, otherwise it gives 0. This is the truth table for 3 inputs OR gate. Sorry. Here only one of the input is 1, so it gives 1, and otherwise all the outputs are 0. And this is the IC for OR gate, which is IC 7486 quad 2 NOR gate. XOR gate. The XOR gate is a digital logic gate that gives the output 1 if both the inputs are of same. This is the truth table for XOR gate. See, if here both the inputs are 0, therefore the output is 1. Here one of the input is not 0. Here the inputs are different, so the output is 0. Here both the inputs are same, so the output is 1. This is the 3 input XOR gate. Here same logic applies to this. Conclusion. In conclusion, logic gates are the fundamental building blocks of digital electronics. It helps in performing complex arithmetic calculations in a simpler way by using AND, NOT, and all the other exclusive, basic, and other universal gates. They also helps in making decisions and helps in storing data. And they also perform binary operations. Thank you.
So very good presentation, Aditya, Alapan and Aniket. So your topic is logic gates, okay? So my first question is, what is the difference between normal gates and logic gates? So next group is Orchita, Ghosh, Orpon Pal, Oyon Manna. Your topic is universal logic gates. Okay, start.
Good morning, ma'am. Today's our presentation topic is based on universal logic gates.
Yeah.
Here is our introduction. What is universal logic gate? Universal means universal logic gates mainly NAND and NOR called as universal logic gates because we can achieve the basic logic gates like AND or NOR through NAND gate and NOR gate. Though they are called as universal logic gates. NAND gate is a basically combination of NOR gate and AND gate. Whenever we are giving the input terminal 0, we are getting 1. And if we are giving the input 1, which means actually when the input terminal is set, output change. Output is the complement of the input, and when the input is 0, 1, output is the complement of the 0. The NAND gate is basically expressed as A dot B, the fourth complement. This is our 3 input terminal AND gate. 4 input terminal AND gate. And here is the IC of NAND gate. NOR gate. NOR gate basically is the combination of NOT gate and OR gate. If we are giving the input such A and B, we are getting the output A plus B that complement. If we are considering about the truth table, then if we are inputting low, we are getting high, and if we are inputting high, then we are getting low. So this is another one of 4 input NOR gate. NOR gate is the IC chip.
Do you remember the chip number? Okay, so when we'll write it, we'll write the chip number, okay? Okay, continue please.
Myself, Oyon Manna. Today I discuss AND gate using NAND gate and the NOR gate using NAND gate. At first we will see the diagram. First we use a NAND gate for input to terminal A and B. Then input terminal is NAND gate means into the A and B input and added a bar means complement. Then opposite NAND gate input is again we complement the A and B bar complement. So our output is A and B bar. Means output when A input is low and B input is low, the output is low. And the second A input is low and B input is high, the output is low. Again A input is high and B input is low, our output is low. And when A input high and B input high, also we have get when output terminal is high input. As you can see, OR gate using NAND gate. OR gate means when we add two input terminal, we use the OR gate. Now this condition we use at first two NAND gate. We need first two NAND gate. One NAND gate input is A and B. Second output we get A plus B complement. And second NOR gate NAND gate input we add the output we convert second input terminal. Output is A and B bar. As you can see the truth table. Next. XOR gate using NAND gate. XOR gate, as we can see the diagram, we use for 5 gate we using one is AND gate and NOT gate we using NOT gate and OR gate one OR gate and one NOT gate. The output of truth table is this, and XOR gate using NAND gate we use at first support our input terminal and we get the NAND gate. Next one. AND gate using NOR gate. AND gate using NOR gate. We make AND gate using NOR gate. At first we get we have two NOR gate. Two NOR gate attached in the series. Because at first our input is A and B and the output A plus B bar means complement. Then our input is A and B. Then again we get output A plus B. The truth table is this. And NOR gate using OR gate using NOR gate. We make OR gate using NOR gate. So we at first we input A and B in the first OR gate means NOR gate. Then we get output is A plus B complement. Then second our input is B means output is A plus B complement. Then our total input is OR gate means A plus B. And NOT gate invert just the complement of the any signal.
As previously discussed by Rahman and Norton Park, we can create universal gates we can create basic gates from the universal gate NAND and NOR, and with that we can also create exclusive OR gate from NOR gate. As you can see from the diagram, we are using first an input and NOR gate for the input which transform the input A and B to A plus B NOR complement, and then we are taking another input NOR gate, two NOR gates to complement to transform that. Then we are again using a NOR gate to using the NOR gate.
So it is group number 3. Your topic is number systems. Vishal is absent due to some reason. Okay. Now Krishna Koli Sharkar and Mohammad Danish. Now please start your speech.
Good morning, ma'am. So today our topic is number systems. So this is the content we discuss: introduction, decimal number, binary, octal, and hexadecimal numbers. At first, what is number system? Number system play a crucial role in digital electronics, enabling efficient data representing and processing computers and digital electronics. Circuits rely on different number systems. At first, what are the number systems? Are the methods of representing numerical values. These systems use a unique base and set of symbols. why are they important? Crucial for understanding the digital electronics and computer architecture, and they are the language that digital devices understand. So first we discuss decimal number system, which is base 10. Explanation uses 10 digits 0 to 9, and each position represents a power. Each position represents a power of 10. And one example is 1, 2, 3. So 1, 2, 3, 4, 5, 6. Each position represents a power of 10. So 1 is 10 to the power 0, 10 to the power 1, 10 to the power 2, 10 to the power 3, 10 to the power 4, 10 to the power 5. So this is an example of
Starting is 10 to the power 0.
10 to the power 0, and 1 into 10 to the power 0, we get the value of
Go to the next slide.
next. Second is binary number system, which base is 2, which use only 2 digits, 0 and 1. One example is there 28. We divided with 2, and the remaining numbers digital on the basis of all digital systems convert decimal to binary. And one example is there 28, which binary number is 1110 and its power is.
Talking about the optional number system, we have 0 to 7 numbers and the base number is 8. So here in the example we see 437, and we have to multiply with the power of 8, that's called 8 to the power 0, that's 1. So 1 into 7, and then 8 to the power 1, that's called 3 into 3, then 8 to the power 2, 64. So total we are getting the number 437 to the power, the base number 8. And in the hexadecimal number, we have 0 to 9, that's 10 numbers, and up to that 8 to F, and the base number is 60. From the example, we can, so here we can see the tables that hexadecimal, decimal, and binary, that the representation, that how we can convert the numbers from octal to binary, octal to decimals. These are the examples. And applications we can use in the memory addressing and color codes. Number system conversions, decimals to binary. While we get a number, to convert it to the binary, we divide with the 2, then we get the remainders, and then we add the remainders, and we get the base number 2. That's called in binary. And in binary to decimal, we get the 4 bits number. If we can take the 3, that's 0, 0, 1, 0, 0, that's the number binary. We take set of 4 bits. And in hexadecimal, we just add the 16 base number. In conclusion, we can say that in digital electronics, we use the main 2 numbers 0 and 1 in binary. And apart from that, we use the hexa and other octal number systems for the for the large binary numbers, we use octal and hexadecimal to represent it in a singular way. So these are the references we have taken.
This will be justified. Okay? This slide. Right, whatever you have the content of this slide should be justified. Your presentation is very good, and your PPT is good because it is a totally background is white and it is totally not black. Now the question is that what is the necessity of number system?
To use the data in a simpler way, convert the data. While we are using digital electronics, we mainly use the 0 and 1.
Maybe you have written, but here yes, change is decimal digit. Base 10 and base 8. Shaktikant Bhattacharya and Nitam Bhattacharya. So your topic is fundamentals of digital systems. So continue, please.
Good morning, and our topic is the fundamental of digital system. Now we are talking about the digital system. Digital system is a type of electronic system that uses digital signals to process and transmit and store data information, and there uses the binary code which is 0 and 1. The fundamental digital system is the logic gates, binary numbers, and Boolean algebra. The logic is there are 7 types of logic gates. The next. The analog and digital system. Analog is a sine wave, and the digital is the square wave. The analog digital system is a represent information stored from is a wave signal. Example is the sound is the best example of analog system because sound uses the amplitude, and digital.
I'm instructing your font size will be little bit larger. Okay. For better visual aspect, the font size will be little bit large. Okay. Continue.
And the digital system is the stored data from the as a binary bit, like the computer, CDs, and DVD. Next. Next is the laws and rules of Boolean algebra. Ritanka Chatterjee will be discussed about that topic. Coming to the laws and regulation of Boolean algebras, there are 3 basic laws: the commutative law, the associative law, and the distributive law. These laws are mainly used to make the circuit short and to reduce the complexity. It also increases the efficiency because when there are number of gates are more and we get the same output, it is better to reduce the number of gates and get the same output. So by these laws, applying these laws to the function, we can get the output, get the resultant function as a less than the given function. Coming to the commutative law, if we for the AND operation, if we use A and B, the AND gate, the 2 input are A and B, so the output we and another gate having AND gate, we can use B and A as an input, then we can get the same output. So we can maintain as A and B equals to B and A. Coming to the OR operations, if we use an OR gate, A and B are the 2 inputs, then we have an output. If we change the input as first one is B and A, we get the same output as the previous one. Coming to the associative law for AND operations, if we use 2 AND gates, and between A and B are the 2 inputs at first, if we get output and that output is attached with the another input of the AND gate with the C, and for another gate, if we use one input as A and another AND gate as an input as B and C, if we align the output in another gate where A is the input and B and C's output will be attached as input of the another gate, then we get the same output as A and B and C equals to B and C and A. So coming to the OR operations, so if we use the OR gate and use the gate as input as A and B, we get the same output. So A and B and C equals to A and B and C or C. Coming to the distributive law, for the distributive law, if we have 3 inputs, if we use a AND gate at first, then A and we use a OR gate where B and C are the inputs, and we get that the AND gate OR gate outputs are attached with the input of the AND gate where A is another input. So we get the same result as A and B or A and C. Similarly for the another law, these laws are used to reduce the circuits, so we can the function can be reduced and we get the efficiency more. The number of gates can be reduced. So by this way we can reduce the time also. So complexity of the circuit can be also reduced. Next.
Good morning, ma'am. Moving further about the topic is laws of Boolean algebra. I will be explaining De Morgan's law. So De Morgan's law It is a set of rules in Boolean algebra that helps simplifying expressions and solve the complex circuital problems. Another point is, it states that complement of the resulting OR or AND gate is same is in variable complements of individual variables. As we can see, theorem 1, if we apply mathematical operators as bar and dot between the two inputs A and B, we can see that A dot B of bar is equals to A bar plus of B bar. Explaining about the truth table, if both of the inputs are high or low, then then only we can get the output. If either of the input is high, then only we can get the output. But if both the inputs are high, we can get the input as 0, the output as 0. This truth table explains that if either of the inputs are high or low, then we will get the output. If both the inputs are low, then we will get the output as 0. Theorem 2, which is bubbled and NOR gate. In this gate, the expression is A plus B bar equals to A bar dot B bar. Explaining the truth table, if either of the input is high or low, then the output is 0. If both Now moving further about derived gates. NAND is basically AND inward. If we apply y equals to A dot B in AND gate, then NAND gate expression comes as A dot B of bar. If we
So group number is 5. Shomam Shaha, Shomojit Seth, Shomojit Wadkar. Your topic is words and use computers and so please continue.
Morning, myself Shom Shah. I am going to speak about what is ones and twos complements. So why do we use these complements of 1 and 2? We use them to get the negative arithmetic operations values of magnitude or extra, and we can use these complements for addition and subtraction. So how to get the ones complement? We can get ones complement by doubling the bit to 0 to 1 and 1 to 0. Like how the example is given of binary number given of 0101, we have the ones complement of given bit as like 1010, flipping all the bits to its form. And then coming off two's complement. Two's complement is nothing else, just adding 1 to the resultant to get the value. Like example, if we see the given binary number is 0101 and we get 1's complement as 1010. Now for 2's complement we need to add plus 1 for the resultant. So we get, so as given how to find the inverted all bits, so we are transferring all the zeros to ones and ones to all the zeros. And the example is the same. The issue of the given ones complement is that for 0 we have two representations that is given 4 zeros and 4 ones in 4 bit. And this two's complement is widely used mostly in the digital circuits. Like how to find it, as the given number is 0101, now for the resultant we are adding 1. So the answer comes for us that 1011. And if we take that the last digit is already given for 1's complement is 1, then the 1 will remain the same. There will be no complement for the 2's complement.
Hello ma'am, myself Suman. The addition using 2's complement. First step, convert the number to binary using 2 complements of negative. Perform the binary addition as usual. Then third step, ignore extra carry for 6-bit operation. We have given an example 5 plus minus 3 into 5 plus minus 3 into 5 plus minus 3 in 4 bits. First step we have to convert to binary. Here we have converted 5 into binary 48. Minus 3, the 2 complement of 3, the 3 in binary 0 0 1 1. 1's complement 1 1 0 0. First in 2 complement we have to add 1 to get the result of 2's complement of minus 3.
What was the problem? Go to the next previous slide, please. How to find 2's complement?
0 1 0 1 plus 1 1 0 1. We have get the result of 1 0 0 1 0. Subtract using 2 complements. Subtraction using 2 complements. Instead of subtraction, convert the subtraction into addition using 2 complements. A minus B is equal to A plus 2 complements of B into A minus B is equal to A plus 2 complements of B. A into A minus B is equal to A plus 2 complements of B.
So basically you are doing the subtraction using 2's complement method.
Yes, ma'am.
Okay.
Here we have given an example of the subtraction using 2 complement. 5 minus 3 in 4th bit.
Using 2's complement method, the subtraction. Alapon, listen.
We have given an example 5 minus 3 in 4 bits binary. First step, we have to convert the number to binary. Mainly we know plus 5 is equal to 0 1 0 1 and plus 3 0 0 1 1. In second step, find 2 complement of 3. 1's complement is, will be 1 1 0. Then we have to add 1 of 1 1 0 1. Then we have to get the then we have to get 2's complement of 3 1 1 0 1. Then we have to add the plus 5 and minus 3. The 0 1 0 1 plus 1 1 0 1. The result we get 1 0 0 1 0.
So if you subtract, go to the previous slide.
Yes.
If you subtract 3 from 5, the result will be?
The result will be 1 0 0.
No. On the decimal process, if you subtract 3 from 5, the result is 2.
Yes, ma'am.
Clear answer. So here, how can you get the result? What you have told here, you are using subtraction using 2's complement method. Okay. So 5 is 0 1 0 1, no problem. Plus 5, I know. Plus 3 is 0 0 1 1. Okay. So you are basically doing 2's complement of hello, listen. So our last group is group number 6. Srijan Shil, Shubhajit Khan and Sharbojit Das. Shubhrojit Das, I'm sorry. So your topic is Boolean algebra.
Yes.
Okay, please continue.
Good afternoon, ma'am. Our topic is Boolean algebra presented by Srijan Shil, Shubhajit Khan and Shubhrojit Das. This is the content of DVD, that's abstract introduction. Yes. Let's first talk about the Boolean algebra. Boolean algebra is basically a binary number used in 0 and 1, and it is used for logical operation, data processing, computers, programming, etc. And Boolean algebra is applied in digital system basically. Yes. Then introduced the Boolean algebra. This method was introduced by George Boole in 19th century. This is a model of logic operation. There are some gates like AND, OR, NOT gate, etc. many more. And this was in two binary digits 0 and 1 respectively. There are some applications about first digital circuit designing, computer programming, and some say theory and data systems. Then the first part is theory. Boolean algebra is basically two-digit number 0 and 1. There are some operations AND, OR, and NOT. So first for AND gate, if we put 2 0 output, 0 input, then I will get 0 output. And basically because of AND is multiply of 2 input. So 0 into 0 we get 0 output. For 0 into 1 we get also 0 output. And for 1 into 0 we get also 0 output. But in case of 1 and 1 output we get 1 output. So basically this is the overall structure of AND operation. Then Subhajit will continue some other operations.
Hello, my name is Subhajit. What this result is the one last of plane is the one formula is the a plus 1 a plus b is 1 1 and a is 1 1 b is 1 1 is equal to 0. This